All right, here we go. Good morning. Welcome to the last day of Cisco Live. There is no Cisco Live without the live, right? So I'm really glad that we were able to come back and do this. Without the interaction, I could not stand anymore any Cisco Live digital, right? It's an aberration. So very, very happy to be back with you. This is the last day. My name is Max Erdic. I'm a distinguished engineer, part of the data center business unit. It's safe to assume that if you're here, it's because probably you attended also the previous session about the VXLAN packet walk. And so what we're going to do in this session is just doing a follow-up built upon that information that Lucas gave you in the previous session and look at the packet walk for a VXLAN multi-site environment. As you can see, the stage, they're putting us more and more back. I was told next year the stage will be behind the screen so that you don't even see us, right? I cannot even see what I'm going to be talking about, but that's probably a good thing. So two things before we start. First of all, packet walks, right? So a couple of months ago, Lucas, my good friend, was like, man, this year we're going to do packet walks. I was like, sure, man. Then we look at the schedule, packet walks, the last day, after the party, I was like, oh man, how can we make something dry as a packet walk a little bit more entertaining? And then I had this illumination. I'm going to present the packet walk with an Italian accent. So I went through 2 months of intensive training to develop this thick Italian accent, right? So now, at the end, you will tell me if my trainer was good enough to give it to me. If not, I'll go back to lessons for next year's Cisco Live. Second thing, I hate, and I repeat, I hate 45-minute sessions, right? I don't know if you guys agree or not. I guess, Lucas, they agree, right? So you come here for an education. Cisco Live is about giving you good content, right? 45 minutes doesn't give justice to any session that aims to give you good content. So as a response to that, and I've done that consistently throughout the week, I went rogue against the system. So my session all lasted 50 to 55 minutes. One lasted even 1 hour, right? So it may very well happen that this happens also today. It is not time mismanagement, right? So you can write that in the report. The speaker didn't manage well the time. It's not that. The speaker is managing well the time. The speaker thinks that this session deserves more than 45 minutes. What you can write, and they will hear you, is that you want back the 1 hour session or 2 hour sessions, right, for content like this that deserves to be clearly explained. Thank you very much. Okay. And after this, I'm going to be fired, so it was good to see you. But anyway. All right. So WebEx room, Lucas is here. He will address any question you may have. This is one of the last VXLAN EVPN session of the week. So again, he built upon the previous one that was presented by Lucas. I'm trying to follow a similar approach, right? So in the end, I change a little bit the order, and I start with the BAM packet walk, with the layer 2 packet walk, because in my mind, two things, right? One is Silvano Gai, who is still alive, a great Italian teacher in a University of Torino of telecommunication, always said, you want to know if a network device is properly built and designed, you need to look how it handles multi-destination traffic, right? BAM traffic. BAM is broadcast and non-unicast multicast, right? And so I'm going to paraphrase what he said, and I'm going to say, you want to know if an architecture is properly built, you need to see how it handles the layer 2 multi-destination traffic. So we will start with the layer 2 BAM, even because what is the first thing that a device does to communicate? It sends an ARP, right? And an ARP is a layer 2 BAM packet, okay? So we'll talk about how BAM is handled by multi-site. In the agenda, I have ingress replication, multicast replication. For the sake of time, I'm going to do only the ingress replication, but you have the slide for the multicast replication as well. Then we'll talk about the layer 2 communication, the packet walk for layer 2 communication between endpoints, and then we go into the layer 3. Layer 3 communication between endpoints connected to different fabrics, different sites, and layer 3 communication with the external world, right? Because nobody builds data centers to communicate with each other. We build data center to host applications that allow external client to come in, okay? And in the end, I will talk about also the silent host discovery, which is an important part of layer 3 communication. And I owe an answer to a gentleman that asked me a question, and I will provide it at that point. I didn't forget. So, quick introduction. I hope if you're here, you also attended Lucas VXLAN multi-site session, but what is multi-site? Multi-site is an architecture that we built to allow you to interconnect different VXLAN EVPN fabrics. And the goal is to give you the capability of extending layer 2 and layer 3 communication in a flexible way between different VXLAN EVPN fabric, but in a flexible but also most controllable way, right? So I want to be sure that I control where and when I want to extend layer 2 between my sites, and I want to be sure that I also control that flooding of traffic between the sites, because if a broadcast storm hits VXLAN EVPN fabric 1, I don't want the broadcast storm to propagate to fabric 2. And so in order to be able to do that, we built this architecture that has basically 3 main components. There is the fabric, and that's usually a traditional two-tier, not two-stage, two-tier VXLAN EVPN fabric with leaf and spine. And the VXLAN multi-site architecture doesn't make any assumption about what these leaf spines are. Whatever they are, as long as they support VXLAN EVPN, they can be part of a VXLAN multi-site architecture. The second component is the external network. There is an external network, however it's built, it's a layer 3 core that interconnects my fabric. Okay, that core is basically an extension of the underlay that allows to build then VXLAN communication site to site. The main actor of the VXLAN multi-site architecture is actually this guy here, the border gateway. Okay, and the border gateway, and we will see in the packet walk, really represent the interface of each fabric with the rest of the world, with the external networks and also with other fabrics. Okay, and so everything that is connected in a fabric, all the taps, all the VTAPs, all the endpoints, they are kind of hide behind that border gateway. And this allows us to build a sort of a hierarchical architecture, both from an underlay and overlay perspective. And the border gateway is actually responsible for stitching VXLAN tunnels built inside each fabric to allow intra-fabric communication, a VXLAN tunnel built border gateway to allow to extend layer 2 and layer 3 communication between the sites, okay? And so the border gateway is really the key component of this architecture. Each border gateway always have 2 addresses at least, a PIP, which is an individual IP address loopback that identifies the encapsulation and decapsulation of traffic originated by that specific border gateway, and a VIP, in this case a multi-site VIP, which is an Anycast TAP address that both or all the border gateway in a site own, which is used to advertise all the local hosts with the next stop being that multi-site VIP. So all the endpoints that are discovered in Site 1 are going to be learned with the next stop, the multi-site VIP of that specific site, okay? And we will see that in the packet walk. Last point, there are 2 types of border gateways. There is Anycast border gateway, there is VPC border gateways. Now, in most of the scenarios, Anycast border gateway is the way to go, okay? And I truly recommend that you deploy that. Anycast border gateway means these border gateways have their own identity. There are layer 3 devices that are not part of any domain or any redundancy domain with each other. VPC border gateway means the 2 border gateways are part of a VPC domain. And there are some specific use cases where that may make sense, like integration with a legacy network, like you want to deploy a small fabric and you don't want to dedicate leaf to the border gateway function. But in that case, you could put the border gateway on the spines, right? But anyway, there are some use cases that I'm sure Lucas covered in the multi-site talk on where VPC border gateway matters. For the sake and purpose of this session, I put, and with that I look at the reference topology. I have two sites, two fabrics, one on the left, one on the right, two different autonomous systems, and I'm using the two types of border gateways, two Anycast border gateways on the left, two VPC border gateways on the right. From the sake and purpose of the packet walk, it makes absolutely no difference if I have Anycast border gateway or VPC border gateway, right? And so that's why I put the two flavor there to show you that makes absolutely no difference, okay? So that's the topology of reference. I have site 1, ASN 65001, with a compute leaf, with the two Anycast border gateways, with a border leaf, which provides connectivity to the external world, because, as I mentioned, we want to cover also that part. And I have a second site with a pair of compute leaf and a pair of VPC border gateways. I don't show spines. The spines are in the middle of that little cloud. And also, probably you're wondering, could I combine some of these functionalities on the same leaf? Absolutely, right? You could have VPC border gateways being also compute leaf. You could have Anycast border gateways being combined with the spines. We have lots of flexibility now you build the topology, but to make you better understand the packet walk, I created these different devices, right? So separated in the slides. So without any further ado, let's start with the BAM packet walk. What is BAM? BAM is broadcast, unknown unicast, and multicast. What is the most common example of BAM? ARP, okay? Now, I'm not talking about specific protocols in the packet walk. We just talk about a generic layer 2 packet, layer 2 BAM packet. And we cover ingress replication, okay? And so what is the expected behavior is, if a host inside one generates a layer 2 BAM packet, I want that BAM packet to be replicated inside my site to reach my local border gateway. The border gateway needs to have some communication between each other to decide who is responsible to handle the replication of the BAM packet to the remote sites. We don't want all the local border gateway to do that function because that would create multiple copies sent to the remote sites. And there is an election that happens in a different way if you have Anycast border gateways or VPC border gateways, which basically determines for each layer 2 segment who is the designated forwarder, who is responsible to replicate that traffic to the remote sites, okay? So the designated forwarder does the replication, send the packet to all the remote sites where that layer 2 VNI has been defined. Obviously, if you have 5 sites and my layer 2 VNI is only stretched to site 2 and not 3, 4, 5, I don't want to send the BAM for that layer 2 segment to 3, 4, 5. It would be useless, okay? So we only replicate to the sites where we know that layer 2 VNI exists. How do we know? The control plane tells us, and we will see, okay? And then the receiving border gateways, also the designated forward in the receiving site will do the local replication, and I will reach all the endpoints in that VNI, right? The beauty of VXLAN and of VXLAN EVPN is to provide that abstraction where devices could be connected in fabric on the opposite side of the world and look like if they were sitting on the same layer 2 VLAN connected to the same switch, right? This is the power of having an overlay, okay? So in order to create that layer 2 extension, I need to define an L2 VNI. The L2 VNI is the VXLAN equivalent of a VLAN. And in fact, a VLAN is always mapped to an L2 VNI. In my case, and this is the important point, we multi-site, I control the extension of layer 2 to remote sites by defining or not defining the L2 VNI on the border gateway. If I want to extend a segment out of my site, I need to define that L2 VNI on the border gateway. If I don't define the L2 VNI on the border gateway, it means that layer 2 segment is local to my site and doesn't need to be extended. So in our example, I have 2 sites, I need to extend layer 2, I want to send BAM across the sites, I define my L2 VNI pretty much everywhere. Okay, on the compute leaf, local border gateway, remote compute leaf. Okay? Now, once I define that L2 VNI, what's going to happen if I configure ingress replication, which is a specific configuration knob that you put on the configuration of the devices will start advertising an EVPN type 3, right? In the type 3, they will advertise the information that they have a locally defined L2 VNI, and they will tell, this is the next stop, this is my PIP address that the other devices need to use to replicate traffic, bump traffic, sent to that L2 VNI. So this exchange of type 3 goes on inside each site and allows essentially the devices to build a flood list, right? In my case, since I want to show a packet going from site 1 to site 2, I make the control plane going from the right to the left. But imagine that the type 3 are exchanged between all the devices in the same fabric and also between the border gateways across the site, okay? Now, in an any-to-any full mesh fashion. And so the local border gateway inside 2 will be the flood list that says, oh, this L2 VNI, when I receive a bump packet, I need to replicate it to the PIP address of leaf 20 and the PIP address of leaf 23, which means these two leaf 20 and leaf 23, have that L2 VNI locally defined. So they may have hosts directly connected that need to receive the bump packet. The border gateway also send EVPN type 3 to the remote border gateway to inform them that actually, yes, there is an L2 VNI defined in my site, so if there is a remotely generated bump packet, you need to send it to me, right? Because I may have hosts locally connected that they need to receive that. And so that's also type 3, with the next stop, the PIP address of border gateway 21, border gateway 22. Now you get the gist, the receiving border gateway build the flood list, and they will put the two remote border gateways in the ingress replication list. Same thing happens inside Fabric 1, and the compute leaf also build the flood list, right? So at the end of this type 3 control plane exchange, every VTEP will have a list that know where to replicate the traffic. And obviously, inside each site, I will have the list that includes all my local leaf where that VNI is defined, plus my local border gateway in case I decide to extend my VNI out of my site, okay? So what happens once the control plane does its job? How does the forwarding work? Well, it becomes quite easy. The host sends the bump frame. The receiving leaf looks at the packet. He looks at the flood list and says, okay, this is a bump packet. I need to send it to all the VTEPs in my flood list. In my simple example, I only have the two border gateway here. So he sends the packet to both border gateway. Because the compute leaf does not know which of the border gateway is the designated forwarder responsible then to replicate the traffic to the remote sites. So both border gateway needs to receive the packet. They receive it, the designated forwarder send it into the remote site, but before doing that, and this is another critical important point, I need to ensure that the border gateway that received the packet do not re-inject the packet inside my local site, right? And so with the VXLAN multi-site, we built this split horizon functionality whereby both border gateway receiving the packet from a link connecting to the internal fabric, we call it a fabric link, will never re-inject that bump packet into another fabric link connecting to my local site, okay? That's a split horizon rule, which is actually a critical functionality and the main reason why we were the first in the market to deliver this VXLAN multi-site solution is because you need to have the proper ASIC to be able to handle this specific functionality, right? To stitch this layer 2 tunnel site to site and apply this split horizon. So the split horizon rule kicks in. In addition to that, the non-designated forwarder drops the packet. The designated forwarder replicates the packet based on the flood list to all the remote border gateway, and here I will have the list of the PIP of all the remote border gateway of all the sites where I extended my L2 VNI, okay? And so both remote border gateway get the packet. Again, split horizon kicks in, not to re-inject the packet now, not inside the fabric, but in what we call the DCI, the external intersite network. And we have on the border gateway the definition of DCI link that define which are the interfaces connecting to the intersite network. So again, same split horizon rule kicks in. Same dropping on traffic from the non-designated forwarder, whereas the designated forwarder replicate the packet inside the destination site based on the flood list that he built, right? And in this case, my packet goes to the two leaf where that VNI has been defined. The leaf at that point get the packet, decapsulate it, and send it down to the endpoint, okay? After doing, also the leaf does the same split horizon rule, okay? Split horizon is something that happens on the border gateway, but also inside each leaf. And you see that there is a lot of intelligence that needs to be built into the system. Remember what Silvano said? How you handle BAM tells you how strong or how well architected a network architecture or a network product is, right? You need all this stuff to happen to avoid duplication of traffic, to avoid bad problem loops to happen, okay? And so, in the end, the packet gets to the two endpoint, okay? And so this is how, with ingress replication, my layer 2 BAM traffic goes from left to right and allows this endpoint to look and feel like they're sitting on the same layer 2 Ethernet segment, okay? Now, question. How do you protect the other side from the first side? There is an issue with the BAM here. Oh, yes, okay. The question, I didn't cover it because, again, I assume that you have some information got already from the multi-site session. How do you protect if there is a broadcast storm in site 1? How do I protect site 2? How do I ensure that all these packets are not replicated like crazy, bringing down my entire multi-site architecture? There is a storm control, aggregate storm control functionality that the border gateway performs. So you can configure for each type of traffic, broadcast, unknown unicast or multicast, a specific percentage. You can say only 10% of the aggregate broadcast traffic generated in the site should be sent to the remote site. Or you could say 0%. I drop all the unknown unicast traffic generated in the site, I will never replicate it to the remote site. So it's a control that you have on the border gateway, and that's why the border gateway is a key actor in this comedy, right? Because the border gateway controls not only if you want to extend a VNI, but also how much of BAM traffic you allow or do not allow out of your site toward the remote destinations, okay? So it's a aggregate. You can think about an aggregate BAM storm control functionality that you configure on the border gateways of each site.
The other question I have, how many VLANs? I mean, is there a recommendation how many VLANs we can extend to the other side? For example, if you go to the system admin, you want every single VLAN to be extended. Let's say you have 200 VLANs. What is there a Cisco recommendation? It says only 10 VLANs or 20 VLANs?
Is there a Cisco recommendation into how many VLANs can you extend across sites? And the answer is, you can extend as many VLANs as we support, right? And so today we support, I believe, is 2,000 VLANs. Is it correct, Lucas, 2,000 VLANs on the border gateway? 3,900. See, things are getting better and better. I even lose track of how good we are. So you can extend 3,900 layer 2 segment out of your site, right? Does it mean that you will have to extend all that L2? Maybe, maybe not. But keep in mind also one other thing, that on the local border gateway, you control how many VNIs you sent out, but also the remote border gateway controls if the VNI, the information for that VNI that I sent is going to be accepted or not, right? So I may have site 1 extending 3,900 VNIs, but site 2, 3, 4, 5, only site 2 accept these 3,900 VNI. The other one don't, okay? So, but you have all the flexibility you want to extend as many segments you need. You won't need more than that, I hope, okay? And if you need, you will have to deploy multiple pair of border gateway, right? You could scope 3,900 on border gateway instance 1, 3,900 on border gateway instance 2, right? Because the L2 VNI segment, you know that we can define, are way more than 4,000 VLANs, okay? Now, enough about BAM. BAM is critical. It's important to handle it properly, but BAM is a mean to a purpose, right? For example, ARP to resolve the ARP information that allows then layer 2 communication to happen. Now, how does layer 2 host to host happen? Well, what we expect, high level from a traffic flow perspective, is that a host will send a layer 2 packet. Let's assume that I did already ARP BAM, so I know to which MAC to send it. The VTEP will know that the MAC is learned through my local border gateway. The border gateway will know that the MAC is learned through the remote border gateway of the remote site where the endpoint is located. The remote border gateway will send it to the local leaf where that MAC address has been discovered, okay? That's what we expect from a high-level flow perspective. Now, more in detail, how does that happen? Again, layer 2 VNI definition. And one important point I want to raise here, do you see any layer 3 VRF definition here? You don't, right? When we talk about pure layer 2, you don't even need to define a VRF. You can just define VLAN and L2 VNI, map the VLAN to the L2 VNI. Lucas talked about MAC VRF table and RIB. You don't need any information in the RIB, even if it is IP layer 2 communication, which means IP address to IP address in the same subnet. You don't need an SVI, you don't need a VRF for that to happen, right? You can really use, and in some scenario may make sense, your VXLAN EVPN fabric as a pure layer 2 network, and in that case, all you need to define are the L2 VNIs, okay? You don't need the VRF. The VRF comes into the picture when you start doing layer 3 routing, and we will see that in a second, okay? So, I define my L2 VNI, we saw it already, so they are defined. Now the host, as a result of the definition, when I basically connect host to my leaf, the local hosts are learned. I learn the MAC address from any packet that this host sends out. The local leaf will learn, oh, I have this MAC address like any switch, right? Like any layer 2 switch. Oh, I'm learning this MAC on this local interface. Once I learn that MAC, what the leaf generates, control plane, EVPN 101, generates a type 2 with the information that, okay, this MAC is locally connected to me. To reach this MAC, the next stop you need to use is my local PIP, right, 10.1.1.10. And that information is propagated inside my local fabric so that the local border gateway gets it. The local border gateway have the L2 VNI locally defined, which means I need to extend out that VNI, okay? And so that means I'm gonna send the type 2 information. I'm going to propagate the EVPN type 2 or regenerate, if you want, a type 2 advertisement toward the remote border gateway with the information that in order to get to that MAC, the next stop is my multi-site VIP, right? Remember I told you all the hosts connected in a site, they're hidden behind the multi-site VIP address, which is configured on the border gateway and identifies that site, okay? So the MAC address, the next stop for that MAC address is the multi-site VIP, okay? And another important thing that the border gateway need to do, they automatically change the route target of this advertised type 2. Why? Because under the assumption that the route target is auto-generated, the route target is always the autonomous system by default, 65001, semicolon, the VNI ID. Now, the VNI ID is consistent in Site 1 and Site 2, but the autonomous system is different. So if the border gateway would not change the autonomous system based on the autonomous system number of the remote site, the remote border gateway would not import that route in the local MAC VRF table, right? So that's why I put in red 65002, because that's a rewrite function that the local border gateway does, okay? So the remote border gateway get the information, put it in their MAC VRF table, regenerate a type 2, forwarded inside the site, the destination site, with the information that sent to everybody that says, hey, when you want to send a packet to this MAC does not exist in your site, you need to send it to me. You need to send it to the multi-site VIP because it's something that I know exists in a different site. Okay, so all the local leaf will know that to get to the MAC, they need to go to the border gateway. It's like a sort of default route, right, to go to that any remote destination. So on the opposite direction, it happens the same for host B information, of course, okay? Now, based on this exchange of information, when the host A sends the packet, we populate the information, right? So if you look at the MAC VRF table, each host, each border gateway knows exactly what is the next stop to reach the MAC, okay? And again, you can replay these on your side. You have all the slides, and you will see that the information that they put in the table is consistent with the control plane exchange that has happened in the previous slide. And so when the host generates the packet destined to the MAC address of host B, the local leaf will look at the packet and will say, okay, to get to this address is not inside my site. I need to encapsulate to the multi-site VIP, which is the border gateway, my local border gateway. Okay, so we do a local site, a tunnel, a VXLAN tunnel local to the site, and we send it to the destination the multi-site VIP. Now, for sure, inside the fabric, you will have multiple paths, equal cost path, through the spine that will take you to the multi-site VIP. So the packet could be delivered to leaf 1 or leaf 2. It doesn't matter. This is not BAM. We don't need any designated forwarder. Only one leaf will always get that packet, because when I route to the multi-site VIP, I go to border gateway 1 or I go to border gateway 2. It's a unicast packet, right? I will never send it to both. So we don't have the problem of designated forwarder here. One of the border gateway here, the top one, for example, gets this packet. We look in this MAC VRF table, we'll say, okay, to get to this packet, to get to this MAC, the next stop is the remote site border gateway. It means that it exists in that remote site. So the border gateway encapsulate, change the destination of the packet to the multi-site VIP of site 2, right? I don't need to know behind which leaf in site 2 is. I don't care. I encapsulate to the multi-site VIP that identifies the border gateway of site 2. One of the core will do is routing, and depending on topology, routing information, one of the border gateway will get the packet. Question? How does it know to which of the remote border gateway is supposed to send the packet to? It does not, because again, it sends it to the multi-site VIP. The multi-site VIP is owned by all the remote border gateway. And at that point, it's just routing that will take the packet to border gateway 1 or border gateway 2. I don't care, okay? That's the beauty of having what we call the Anycast step address, which is an address, the multi-site VIP in this example, that is owned by all the border gateway of a site, okay? And it's basically the interface for traffic from the local site to remote and from remote to local, okay? So in this case, the border gateway on the bottom, the 20, I'm blind like a bat, border gateway 22 is getting the packet. He will then look in his MAC table, and now in his MAC table, he will see that, oh, this MAC is behind the local leaf, right? And he will encapsulate the packet, decapsulate, do the layer 2 lookup, and re-encapsulate the packet to the local leaf PIP address. And the leaf will then decapsulate, look in the MAC table, I will have my local host learn, and send it to the local.
So, if I understand correctly, either in the source side, ECI, and destination side, we always leverage the ECMP to deliver the packet to the source border gateway and to the agent neighboring gateway, and to eventually do the
So the comment, do we always leverage ECMP to send the packet local leaf to local multi-site to remote, local border gateway, sorry, to remote border gateway? The answer is, inside the fabric, for sure, you will have many ECMP paths. In the external network, it depends on the topology you built, right? You could, for example, connect the border gateway 3 sites with border gateway back-to-back. In that case, you wouldn't have equal cost. You will have, if you want to go to site 2, you have a direct link. If you want to go to site 3, you have a different link, right? It depends on the topology. It's basically IP routing. In a destination site, is equal cost to the leaf, for sure, through the spine, right? You will have the local leaf, you will learn that PIP via all the local spine, probably, that you have connected the border gateway to.
But our PIP is the multi-site PIP, right? When we sending from
Site 1, correct.
Based on that multi-site PIP, underlying routing will decide which one to do.
Absolutely. Based on the multi-site VIP destination, the underlying routing will use equal cost path if I have, or not if I don't have. It depends how the network is built.
Hypothetical, I want to go crazy.
He wants to go crazy, he said. Stay tuned.
Both sides only layer 2/16. 1 million hosts. I'm there.
Yep.
Since there's no flooding, no broadcast, everything is unicast. So everything is going to be translated to be unicast. Can I do this one?
Can I go crazy and build a huge, gigantic network, right, /16, only layer 2, and since I can control flooding, can I have this gigantic network with so many endpoints all connected? As long as there is a limit on points that you can store, right, because MAC tables have a limited size, but 90K, right? So if you stay behind, because then if you cannot put any more MAC address information in the MAC table, what's going to happen?
You're not going to forward traffic.
you're going to flood, right, at that point. And if you drop the flooding between sites, it will not work, right? So as long as you don't fill your MAC table, and modern devices have big tables, right? It is doable, absolutely. Now, would you want to do it as /16 layer 2 subnet? Don't come back to me and Lucas after you're done and say, oh, it's a bit chatty, yes. Huh? He shouldn't cause, you're right? It's not like deploying a /16 subnet in the same fabric, right? Where you will have a lot of, stuff going on, right? Here, you have control, you don't broadcast across sites, you can avoid that. So it will be a more stable environment. Still, I will lean toward the crazy idea more than a good thing to do. But yeah. Everything is doable. But okay, if you want to do it, divide the fabric in multiple fabric and use this approach, for sure, if you want to go down the path. Okay, need to accelerate a bit because I'm going rogue to the system, but there is a limit, then they will come and grab me out of the stage, probably. So let's move into the layer 3. But now you get the gist, and so you should be easier to accelerate a bit. Now, in layer 3, what we expect, from a traffic flow perspective, we expect exactly the same flow, left to right, that we saw for layer 2, right? What is changing is that when I go into the definition of VNIs, now I define an L2 VNI, and I also define an L3 VNI. The L3 VNI is associated to the VRF, right? So since I want to route, what I need on my leaf, on my compute leaf, is a default gateway function, right? So I need to instantiate the VRF, I need to instantiate the SVI that represent the default gateway for the local endpoints that are part of the L2 VNI. But the interesting thing is that if I only want to route across site, and you will see when I do this, what is different in this slide compared to the one I show you for the layer 2? Is that the L2 VNI is only defined on they're only defined on the compute leaf. I have two different L2 VNI, one for associated to VLAN 10, one associated to VLAN 20. I don't want to extend this VNI across sites. I just want to use VXLAN multi-site for routing, right? Subnet to subnet. So what I need to extend is the L3 VNI, the VRF. And I do that by defining the VRF also on the border gateway, as you see here. If I didn't define the VRF on the border gateway, that VRF will not be extended, and everything I show you in the next 5-6 slides will not work, because the control plane would not exchange information between the sites. But if I want to extend the VRF, if I want to route between two fabrics, I define the VRF on the border gateway, and this will basically trigger the control plane that I'll show you later, right? And that's why I said at the beginning, the border gateway is the key component that allows you to control what you extend across sites. If I define the L2 VNI on the border gateway, means I want to go layer 2 to a remote site. If I define the L3 VNI on the border gateway, means I want to go layer 3 across sites, okay? And that's the level of control you gain with this VXLAN multi-site architecture. Now, from a control plane perspective, if you do this configuration here, BAM across site doesn't work. No, because you don't need. Why do you want a BAM if your VNI is only local to the site? You do BAM inside your site, right? And that's the beauty of using this just for routing, if you want, okay? Now, from a control plane perspective, when I learn my local endpoint, host A connected to the VTEP on the left, I'm still gonna send the type 2. The type 2 now will contain the MAC address and the IP address of that host, right? But what I'm gonna send also is a type 5. And I'm gonna send the type 5 if I configure the leaf to advertise that type 5. That type 5 is the subnet associated to the L2 VNI, okay? And we will see in a few minutes why it's important to define that subnet and advertise that type 5. It has to do with silent host discovery, mostly, okay? So I advertise the type 2, I advertise the type 5. The border gateway, what does he advertise to the remote sites? Does he need to advertise the type 2? Yes or no? No. Why? Because we do not extend layer 2. So why do I want to send you granular /32 information to the remote sites? I know that the subnet is only local to my site. So what do I send you? I send you only the type 5. If you want to talk to anyone in that subnet, just send the packet to me for the entire subnet, because that subnet is only contained in my site. This will change as soon as I define the L2 VNI on the border gateway. At that point, the border gateway will start sending out also type 2, because it means someone else will need granular information. The subnet is stretched, and I want them to send the traffic to me only for endpoints of that stretched subnet that are defined or discovered in my local site. But in this case, type 5 is all I need. Everybody who wants to talk to the subnet, send the traffic to me, okay? The difference between type 2 and 5 is in type 2 you have /32 information, so host information. In type 5 is prefix, LPM, subnet information, okay? So remote border gateway gets the packet, same rewrite of an autonomous system number for the reason I explained before, no difference. The remote border gateway sends the packet, the type 5 propagates it inside the site. Opposite direction, the same happens for the subnet that is locally defined in site 2, so that the type 5 information is propagated all the way to site 1. Now, based on that, what I will have in the tables of the devices is, if I look at the compute leaf in site 1, it will have the local subnet, it will have the local endpoint, and also all the other local endpoint learn, and it will only have for the remote subnet the /24 information. With the next stop, the local multi-site BIP, right? If I look at the RIP table of the multi-site local border gateway, I will see that I learned the subnet from the remote border gateway. With the next stop, the multi-site BIP of site 2, right? So pretty simple, quite similar to before in terms of control plane, but with a different type of information exchange between the sites. And as a result of this, what happens when the host 1 wants to send the packet to the host B? Now they're in different subnet, right? So first thing will happen is ARP for the default gateway, which is my local leaf. I resolve the ARP, I send the packet to the destination MAC, which is my local gateway MAC, okay? It's just routing. The local gateway, my local leaf gets the packet, remove the layer 2 header, looks at the layer 3 destination, he knows that I learned that /24 through my local border gateway, send the packet to the multi-site VIP. It goes to one of the local border gateway. The local border gateway looks at the RIP table. I learned that type 5 from a remote site. I encapsulate to the multi-site VIP. Like before, the network takes it to one of them. The remote border gateway looks at the table. The remote border gateway in the table will actually have the specific /32 because I have already discovered host B, and so it will encapsulate the packet to the local leaf where that host B is connected, okay? And then the leaf will deliver it. Now,
so based on how we hear, isn't that just like a hierarchical routing? You have the backbone and you have
yes. The comment is, it is sort of a hierarchical routing. You have the backbone, you have the local leaf, absolutely. And that's the whole point of building hierarchy. I said at the beginning, multi-site build hierarchy in the underlay because I don't send TAP addresses everywhere, and also in the overlay because I send information in a kind of a hierarchical way, right? Local leaf to local border gateway to border gateway, border gateway to local leaf. Exactly. It's in line of traditional hierarchical routing that we have been advocating. Was that? Yeah, well, and as Lucas pointed out, but also for layer 2 communication, which is the big difference, right?
If you have a multi-site environment where you've got 3 sites and you have a network in site 1 and 2, but not in 3, if you're just advertising the type 5, if you have a host miss where you go to like a host is only in site 1, so you follow the type 5 to site 2, and then it doesn't know where the host is.
That goes to the realm of silent host discovery that we're going to cover now, right? So, and I'll repeat the question because the answer is going to be explained now. I said something when I got to this point which was important, right? When the border gateway inside 2 gets the packet, I said he knows where host B is connected because host B was discovered. So he can encapsulate, so in his RIB, he has a /32 entry, which is learned from a local type 2, to send with the next stop the local leaf, right? What if he doesn't? What if he knows that the subnet is in its own site, but the host B or another host has not been discovered? What if the destination of the packet is what we call it as a silent host? And by the way, the time is over, and as I said, I go rogue and I continue. I don't take it personally if you leave. There is the recording, right? But I will continue for 5, 10 more minutes because I want to finish, okay? So I don't take it personally if you leave, feel free. So my good friend Victor Moreno, that used to work for Cisco, was saying, oh, silent host Max only exists on slides, okay? And maybe it's true, but I guarantee you if we didn't deliver an architecture that handles silent host, there would have been many problems in the field, in real life deployment, right? So we need to handle the scenario where I don't know where my destination is connected, where my destination host is connected. So what happens with silent host discovery? So the RIB table are configured like before based on the type 5 exchanges, the same scenario routing, right? But now, the difference is that when the packet gets to the border gateway in site 2, the border gateway in site 2, he has a local RIB. In the local RIB, he has the /24. He has the /32 for host D, which is 2.10, but he doesn't have the /32 for the host E, which is 2.20, right? So he knows that the local subnet, the /24 is defined behind both VTEPs, and you see the /24 has 2 next stop, right? 2 PIP next stop, which are the PIP of leaf 20 and leaf 23, but he doesn't know where the specific 2.20 is. So now, how do I send the packet to the right leaf? I have 50% of the chance of sending it to the wrong one. And in fact, in my example, I send it to the wrong one. Now the gentleman asked the question, in this example, couldn't the leaf, the border gateway, since he knows that he doesn't know the specific, he knows that the /24 is behind 2 VTEPs or more. Actually, I'm gonna say that in a second, sorry. Let me get back. Let me first go to the end. Let's say that I pick leaf 1 because I follow the /24. I go to leaf 1, okay? Now leaf 1 gets the packet. He doesn't have the 2.20 locally defined, and I made a mistake on this animation. So the VTEP, local VTEP, doesn't have the /32 for that host. He has only the /24 and the /32 for the local host. So what happened is there is a miss. There is a miss. The miss means I need to try to find out where the host is connected, right? And as Lucas explained, what the leaf will do a glean process. In order to discover if that specific 2.20 host exists and where it is located in my site, it generates an ARP request for that host. That ARP request is propagated inside the site, and if the VLAN, by the way, was delivered across, was extended to another site, will also be propagated, like BAM we show across different sites. No matter where that 220 is located in that segment, it will receive this ARP request. It will be forced to respond to the ARP request. And when I respond to the ARP request, I will learn that that host is behind the leaf in this case, leaf 23, okay? So I now discover, I force the Sicilian host to actually talk, right? He was not talking, but I forced him to talk. And so now has been discovered. If there are Sicilian here, don't get it badly. We are all Italian, and it's a joke of not talking, right? I didn't see, okay. Don't give me a bad score for that. I already got nasty comments. I need to get better on that. Okay, so point is, I discover my local host in leaf 23, and then the type 2 advertisement goes on. So that information is now propagated to the border gateway, to my local border gateway. No? So the local border gateway here gets the information 220 is behind tap PIP 23. Okay, now I discover it. Now the question that was asked was, why does the border gateway, when he got the packet, if I go back 1 second here, when he got the packet, why didn't he since he didn't know the 2.20, but he knew that the /24 was behind multiple local leaf, why didn't do the glean directly, like wrongly I put in actually in this slide? And the reason is because the L2VNI is not locally defined, right? We don't extend the layer 2 VNI across sites. If that layer 2 VNI was locally defined on the VTEP, the glean would have happened directly from the VTEP. And in the example that Lucas did in his slide in the previous session, it was the same, right? The leaf where the packet was originated had multiple /24, but it didn't have that layer 2 VNI locally defined. That's why the glean happened on the destination leaf and not directly on the source leaf. Okay?
Doesn't that reduce efficiency? If he can do it, why not, right?
If he can do it, but if he doesn't have an L2 VNI locally defined, he cannot do it, right? So that's the thing, right? So, okay, so let's go back. The type 2 has been discovered. My local border gateway learns it, which means the poor host A continues to send the packet. When it gets to the border gateway, now I know where my /32 is when I get to site 2. I follow the /24 all the way to site 2 border gateway, and now the border gateway knows and sends it to the local PEP, and is delivered. Okay? That's how I force the silent host to basically be advertised. Last 5 minutes, I promise. Layer 3 to the external world, but now you are masters of packet walks, so this should be like a walk in the park. So in this case, I have a border leaf in site 1 connected to the external world. You may think, what happens if I have a border leaf also in site 2? Yes, you can have all possible scenarios, right? You don't need to have connectivity to the external world centralized in a site. You can have a shared border design. You could have what we call it L3 out in ACI terms, but okay, a connection to the external network in each specific site. Most likely what will happen is, if you learn the same external destination in local L3 out connection, you will probably use that local way out. Why? Because I have different autonomous system across sites, and so the IS path usually shorter toward my local border leaf instead of going to the remote border leaf. But rest assured that if the local border leaf failed or are not there, like in the example here, I can always use the border leaf of a remote site to get out. Okay? It's basic routing. So what we expect to happen is that the compute leaf in site 1 will encapsulate to the local border leaf to talk out, and the compute leaf in site 2 will go through the usual path, border gateway, border leaf, to send the packet out to the external network. Now, how does it happen? Obviously, this is another case where it's all about type 5, right? Again, I don't extend L2 VNI. I have local VNIs defined in site 1 and site 2. I receive, with an external peering, my external prefix, 172.16.10, I receive it on my local border leaf. I can use whatever protocol I want, OSPF, ISIS, EIGRP, BGP. Lucas is very opinionated on the fact that you should use BGP, and I fully agree. BGP is the way to go. But however you do, from the external peering, I learn the external prefix. The external prefix is advertised inside my local fabric using the type 5. So everybody in my local fabric that has that VRF defined, the VRF needs to be defined, will import that and install it in the local RIB. Okay? The border gateway also, they are responsible of the propagating and regenerating that type 5 to the remote site, to all the remote site border gateway where the VRF has been defined will import that information and install it in the RIB. If I don't define the VRF on the remote border gateway, I will never learn about the subnet, because it means simply that I don't want remote site to extend the VRF into my site. That's the level of control, again, the border gateway gives you. So the border gateway in the remote site then also propagate the type 5 inside the site, right? And all the next stop are always the proper next stop for multi-site to work. And so at this point, when the host inside 1 sends the packet to the default gateway, which is the local leaf, the default gateway will do the layer 2 lookup, and it will know that, to get to this external prefix, I need to encapsulate to my local border leaf, to the PIP address of my local border leaf. right? Because that's the border leaf that announced that prefix. And the local border leaf will send the packet out. In the remote site, the host wants to send the packet to the external world, goes to his own local default gateway. The local default gateway does the lookup. How do I get to the external prefix? Well, I don't have a local L3 out. So I don't have any local border leaf that told me can get there. But there is the local border gateway that told me he knows of a guy, of a site, where that prefix, that connectivity to that prefix is available. So I encapsulate to the multi-site VIP of my local border gateway. Local border gateway, get the packet, decapsulate, layer 3 lookup. Where did I learn that prefix from? From site 1, which is connected with an L3 out to that external network. So again, encapsulate to the multi-site VIP, go to one of the border gateway in site 1, border gateway in site 1 does the lookup. How do I learn that information? To my local border leaf that send me the external prefix with an EVPN type 5. And the packet at this point goes to the local border leaf send it out. Now there are many variations of these. If I have a stretch subnet and I have L3 outs in each site, I could do asymmetric, how do I avoid asymmetric routing? We have host-based routing for that. So there is more to this, right? And we covered this in the multi-site paper. But in the simplest form, connectivity to the external world is as simple as this, right? Once you understand the dynamic of multi-site, the use of the multi-site VIP, it's basically all the same for layer 2, layer 3, internal and external, okay? Conclusion, there is a question, yes?
So how did the border gateway discover each other? The full mesh configuration?
How do the border gateway discover each other? The border gateway don't need to discover each other. The border gateway needs to exchange information with each other, like if I need to replicate to you because I extend the layer 2 VNI, I use EVPN type 3. If I need to send the traffic to you layer 2 to a MAC, you send me a type 2 or a type 5 if I need to route to you, right? So there is not, and then there is also from a control plane perspective, in order to send you the information, it's a BGP neighbor configuration. It's eBGP, EVPN overlay configuration. You are my neighbor, and we do a full mesh control plane peering, or we do route server. There is a route server functionality. I can deploy the route server in the intersite network, and it's like a route reflector for eBGP. That's what the route server is, right? So I need to build a control plane, and then I exchange all the information, okay? So there is a question from the lady. Can we address this offline if you don't mind, because I need to close, sorry. But come and we'll talk about it. So, conclusion. It was dry, it was a packet walk. I hope it was informative. I hope the thick Italian accent worked for you. If it doesn't, I will try to do a French accent at next Cisco Live, and we try like that, okay? So, as Lucas said, these are a reference. We have amazing prices for you if you fill the survey. The highest the score you give, the most amazing the prices become, right? They're really incredible. I couldn't believe when I saw them. So, please, but jokes apart, tell us if you like the packet walk. If you don't like the packet walks, say, you know, guys, on Friday I want to go to the pool, it's better. We all agree. But if you like the packet walk and they are useful, let us know, and we will repropose this session for future events, maybe improved or expanded. Okay? Thank you very much, and have a safe travel back home.